You are falling. Not toward a mountain, not toward an ocean, not toward anything that has a surface or a shore or a bottom you might someday reach and survive. You are falling toward Jupiter, and the thing that makes this specific terror unlike any other is that Jupiter has no surface. There is no ground to hit, no impact that ends the fall. Just a planet that becomes, by imperceptible and then very perceptible degrees, increasingly dense, increasingly hot, increasingly pressurized, increasingly strange, until the concepts of solid and liquid and gas dissolve into something for which human languages have no word, and you dissolve with them. Jupiter is the largest planet in the solar system, 11 times the diameter of Earth, 318 times its mass, a volume so large that more than 1,300 Earths would fit inside it. Yet, if the Sun is the dominant object in the solar system, Jupiter is the second most important, a body so massive that its gravitational influence shaped the formation of every other planet, shepherded the asteroid belt, captured and ejected comets, and almost certainly played a role in making Earth the kind of place where life became possible. Without Jupiter, the inner solar system would be a very different and probably more hostile environment. Jupiter is, in a real sense, Earth's gravitational guardian and also its most terrifying neighbor. What Jupiter is made of, what happens at each level of its interior, and what any object, including a theoretical human being, would experience during the descent has been studied for decades and most comprehensively by the Juno spacecraft, which has been orbiting Jupiter since 2016 and which, through its microwave radiometer and gravity field measurements and radio occultation soundings completed through early 2025, has revealed an interior structure more complex and in some ways more disturbing than anything predicted by pre-Juno models. Here is what happens when you fall into Jupiter. The fall begins in the outer solar system, approximately 778 million kilometers from the Sun, which appears as a bright but distant star rather than the overwhelming disk you are accustomed to seeing from Earth. Jupiter is enormous even from a distance, a disk visible to the naked eye from Earth, the brightest object in the night sky after Venus and the Moon, a world with bands of cloud visible in ordinary binoculars. As you approach, the disk expands. So the cloud bands, the alternating belts and zones of ammonia clouds that give Jupiter its characteristic striped appearance, resolve into complex structures, swirls, vortices, festoons of dark material trailing from the equatorial belts, and the single most recognizable storm in the solar system, the Great Red Spot, an anticyclonic vortex larger than Earth that has been continuously observed since at least 1831, and that may have been present for centuries before that. Jupiter's magnetosphere, its magnetic field bubble, generated by the circulation of metallic hydrogen in its deep interior, extends 600,000 to 2 million kilometers in the direction facing the Sun and reaches beyond Saturn's orbit in the direction facing away from the Sun. It is the largest structure in the solar system after the heliosphere. As you approach, you are entering a zone of intense radiation. Electrons and protons trapped by the magnetic field and accelerated to nearly relativistic velocities, concentrated in radiation belts far more intense than Earth's Van Allen belts. The radiation environment around Jupiter is the most severe in the solar system outside the Sun itself. The Galileo probe, which became the first spacecraft to enter Jupiter's atmosphere in December 1995, was designed to withstand the equivalent of 150,000 rad of radiation during its approach, enough to kill a human being many times over within hours of entering the system. By the time you reach the upper reaches of Jupiter's atmosphere, you have already received a radiation dose that would be fatal to any unprotected human. But for the purposes of this account, assume you are protected, enclosed in a hypothetical vessel of sufficient engineering to survive what the physics permits, and to experience and record what happens rather than simply being killed by the first thing that tries to kill you. This fiction is necessary because the alternative, the accurate account of what unprotected biology would experience, ends before the interesting physics begins. The top of Jupiter's atmosphere is defined, by convention, at the level where the pressure equals 1 bar, the atmospheric pressure at sea level on Earth. This level is approximately 350 kilometers below the visual cloud tops, the level where the Jovian cloud bands are visible from outside. At the visual cloud tops, the pressure is roughly 1/10 of 1 bar. The temperature here is approximately -145 degrees Celsius, cold, odd but warmer than you might expect, given that Jupiter receives approximately 4% of the sunlight that Earth receives. The upper atmosphere of Jupiter is actually warmer than it should be based on sunlight alone. Juno's measurements have shown that the upper atmosphere reaches approximately 426 degrees Celsius in places, far above the value predicted by models that account only for solar heating. Something else is heating it. The most likely source is the dissipation of gravity waves propagating upward from the deep atmosphere, atmospheric sound in a sense, converting kinetic energy to heat high above the cloud layers. The cloud deck itself begins at approximately the visual cloud tops and extends downward in layers. Yet the uppermost visible clouds are ammonia ice crystals, the bright white material that reflects more than half the sunlight reaching Jupiter, making it the second most reflective planet in the solar system after Venus. Below the ammonia ice layer, at depths corresponding to pressures of a few tenths of a bar, is a layer of ammonium hydrosulfide clouds, a compound of ammonia and hydrogen sulfide that forms tan and brown particles and is responsible for the darker belt colorations visible from Earth. Below that, at depths corresponding to pressures near or slightly above 1 bar, is a water cloud layer, the deepest of the 3 main cloud layers, detected by the Galileo atmospheric probe in 1995 and characterized further by Juno's microwave radiometer. This is the region through which you are now falling. The clouds are thick, not the translucent cirrus clouds of Earth's upper troposphere, but dense convective towers of ice crystals and liquid droplets churning with the thermodynamic energy of a planet that generates approximately twice as much heat as it receives from the Sun. Jupiter is still cooling from its formation 4.5 billion years ago, contracting at a rate of a few centimeters per century and releasing the gravitational energy of that contraction as internal heat. The upwelling of this internal heat drives the atmospheric circulation, the jets, the vortices, the storms that can be larger than Earth and persist for centuries. Lightning is occurring around you. Jupiter has lightning, detected first by Voyager 1 in 1979 and characterized in unprecedented detail by Juno. Odd Jovian lightning is fundamentally similar to terrestrial lightning. A charge separation builds up in the water cloud layer as ice and liquid water particles collide and exchange charge, and the accumulated charge eventually discharges in a massive electrical spark. But Jovian lightning is more powerful than its terrestrial counterpart by orders of magnitude. Individual lightning bolts have been detected by Juno at energies comparable to the largest so-called superbolts on Earth, the most energetic terrestrial lightning, and they occur preferentially near the poles and in the convective updrafts at the edges of the zones and belts. Radio emissions from Jovian lightning have been detected from Earth-based radio telescopes for decades. As you fall below the water cloud layer, the atmosphere becomes a uniform fog of hydrogen and helium with trace amounts of methane, water vapor, ammonia, and other molecules. The pressure is increasing. At 50 kilometers below the water clouds, approximately 400 kilometers below the visual cloud tops, the pressure is approximately 5 bars. At 200 kilometers below the water clouds, the pressure is approximately 20 bars and the temperature has climbed to approximately 150 degrees Celsius. The atmosphere is becoming dense enough to provide significant buoyancy. You would be falling more slowly than in the thin upper layers, the surrounding gas pushing back against your motion with increasing resistance as the density increases. The Galileo atmospheric probe, which is the only human-made object to have entered Jupiter's atmosphere, provided direct measurements down to approximately 24 bar and 160 degrees Celsius before it was destroyed. During its 58-minute descent, it measured winds of up to 530 kilometers per hour, the fastest sustained winds ever directly measured in a planetary atmosphere. The probe entered during a relatively dry region, called a hotspot, where air was sinking rather than rising, and the water abundance it measured was lower than expected. Juno's microwave radiometer, which can probe deeper than the Galileo probe reached, found that the water abundance increases substantially below the probe's maximum depth, suggesting that Galileo's measurement was not representative of Jupiter's global composition. At approximately 1,000 bars of pressure and approximately 1,000 degrees Celsius, something qualitative changes. The boundary between the atmosphere and the interior of Jupiter is not a surface. There is no solid or liquid layer at the bottom of the atmosphere where the gas stops and something else begins. Instead, the atmosphere gradually becomes a fluid. The gas, predominantly molecular hydrogen, dihydrogen molecules, each consisting of two hydrogen atoms bound together, is compressed to densities where the distinction between gas and liquid becomes meaningless. The individual molecules are so close together, colliding so frequently, that the material behaves like a fluid rather than a gas. You are no longer falling through atmosphere. You are falling through something more like a very hot, very dense ocean. At this level, you have descended approximately 0.7% of Jupiter's radius, roughly 500 kilometers. Jupiter's radius is approximately 71,000 kilometers at the equator. You have barely begun. Continue the descent. The pressure increases, the temperature increases. The hydrogen becomes increasingly dense and increasingly hot. At depths corresponding to pressures of tens of thousands of bars, the molecular hydrogen is being compressed so intensely that the electron orbitals of adjacent molecules begin to overlap. The electronic structure of the hydrogen changes. The molecular hydrogen begins to transition toward atomic hydrogen, individual hydrogen atoms whose electrons become delocalized, no longer bound to any specific nucleus, but moving freely through the material like the electrons in a metal. This is metallic hydrogen, a state of matter that does not exist anywhere on Earth's surface under natural conditions. That has been produced in brief flashes in laboratory shock experiments, but has never been maintained in a sustained state. It was first theorized to exist inside gas giants in 1935 by Eugene Wigner and Hillard Bell Huntington. Juno's gravity field measurements have confirmed its existence and provided the first detailed information about the depth at which the transition occurs and the properties of the metallic hydrogen layer. Metallic hydrogen is electrically conducting. It flows like a fluid, but it conducts electricity like a metal. And because it is in a conducting fluid that is rotating with Jupiter's rapid 10-hour rotation period, the fastest rotation of any planet in the solar system, it generates Jupiter's magnetic field. The circulation of metallic hydrogen in Jupiter's interior is the dynamo process that creates the most powerful planetary magnetic field in the solar system, approximately 20,000 times stronger than Earth's. Every aurora that lights up Jupiter's poles, visible to the Hubble Space Telescope as the brightest auroras in the solar system, powered by currents far exceeding the energy of any terrestrial aurora, is driven by the motion of metallic hydrogen in the deep interior. You are inside that dynamo now. The magnetic field intensity at this depth is beyond anything that can be expressed in terms that convey physical intuition. The forces on any magnetically susceptible material are immense. It's the motion of the surrounding metallic hydrogen is slow on cosmic scales, but powerful on engineering scales. Vast laminar flows of electrically conducting fluid carrying enormous currents. The interactions between these currents and the magnetic field they generate produce the complex asymmetric magnetic field structure that Juno's magnetometer has been mapping since 2016. A field that is not a simple dipole, as Earth's field approximately is, but a complex multipolar structure with features whose origins are still being studied. At pressures of hundreds of thousands of bars and temperatures of thousands of degrees, the metallic hydrogen extends through most of the interior. At the center, something else was expected, a compact solid core of heavy elements, rock and ice, the material from which the solid planetary embryo formed before Jupiter swept up its enormous envelope of hydrogen and helium. Juno changed this picture. The gravity field measurements made during Juno's close approaches to Jupiter, the spacecraft passing within approximately 4,000 kilometers of the cloud tops during its polar orbits, provided the most precise measurements ever made of Jupiter's gravitational potential, sensitive to the distribution of mass in the interior. When theorists tried to fit these measurements with models containing a compact solid core, they found that no model with a simple solid core could match all of Juno's data simultaneously. The best models, including the 2024 Neural CMS Deep Learning Analysis published in Astronomy and Astrophysics in December 2024, require what theorists call a dilute core, an extended region of enriched heavy elements that is not a sharp solid object, but a diffuse zone occupying a substantial fraction of Jupiter's interior, blending gradually into the overlying metallic hydrogen rather than having a well-defined boundary. The dilute core extends to approximately 30 to 50% of Jupiter's radius. It is composed of an elevated concentration of heavy elements, rock-forming materials, water ice, carbon compounds, dissolved and mixed into the hydrogen and helium of the interior. The central pressure within this zone exceeds 45 million Earth atmospheres. The temperature exceeds 30,000 degrees Celsius, approximately 5 times the temperature of the Sun's photosphere, the visible surface of the Sun. Not as hot as the Sun's core. Yes, where nuclear fusion occurs at 15 million degrees Celsius, but far hotter than any region of the Sun that emits the light we see. You have fallen to the center of Jupiter. There is no surface here. There is no final impact. There is only the progressive transition from gas to fluid to metallic conductor to the dilute core of heavy elements, under pressures that no material engineering has ever approached, at temperatures that would vaporize any element, in a region so dense that the concepts of solid and liquid and gas have been replaced by something that physics describes as a mixed state, a dense plasma, a region where the distinction between different phases of matter has dissolved as completely as everything else that enters it. The descent took roughly an hour, and in the hypothetical accounting of a theoretical fall from the cloud tops at the rate set by Jupiter's gravitational acceleration of 24.8 meters per second squared, 2.5 times Earth's surface gravity. In practice, no fall through Jupiter could take only an hour because the increasing atmospheric density decelerates any falling object long before it reaches the metallic hydrogen layer. The Galileo probe, which entered at approximately 47 kilometers per second and decelerated to a terminal velocity in the dense atmospheric layers, took 58 minutes to reach its maximum depth of 24 bar before its communication relay was lost, and it was eventually destroyed by the increasing pressure and temperature of the depths. On a theoretical fall to the center at freefall velocity, ignoring the increasing density that would decelerate any object, would take approximately 43 minutes. The actual time for any object to descend through the atmosphere to the metallic hydrogen transition would depend on its size, shape, and density. Any object the size of a spacecraft or human body would reach terminal velocity in the upper atmosphere and would then be carried downward much more slowly by convective currents and slow gravitational settling rather than by freefall. The specific way in which Jupiter kills its visitors depends on which layer they have reached. In the upper atmosphere, above the cloud layers, the temperature is already far below anything human physiology can survive without protection, negative 145 degrees Celsius. The radiation from the magnetosphere would be lethal to any unprotected human within hours of entering the system. Any electronics not specifically hardened against the radiation environment would fail. In the cloud layers, the pressure approaches and then exceeds 1 bar. Human beings can survive pressures of several bars without special equipment. Deep sea divers operate at pressures of 4 or 5 bars. But the pressure increases rapidly with depth, and at 10 bar, the nitrogen in unprotected human tissue would begin to cause nitrogen narcosis. At 20 bars, nitrogen becomes toxic. At higher pressures, without a pressure suit or a rigid hull, the body would be compressed as the surrounding pressure overcame the structural rigidity of bones and tissue. Below the clouds, at pressures of hundreds of bars, no material currently engineered for pressure vessels could survive intact. The Galileo probe's titanium and aluminum pressure vessel failed at 24 bars, far short of the depth at which metallic hydrogen begins. Any vessel attempting to reach the metallic hydrogen layer would need to withstand millions of atmospheres of pressure while simultaneously managing temperatures of thousands of degrees, in a corrosive environment of ammonia, hydrogen sulfide, water, and other reactive compounds. No such material exists. No engineering principle currently understood would permit its construction. If somehow the pressure and temperature problems were addressed, if a hypothetical material of sufficient strength and thermal tolerance existed, the vessel would eventually encounter the metallic hydrogen transition. Yet here, the challenge is not merely pressure and temperature, but electromagnetic. The metallic hydrogen is a conducting medium, carrying enormous currents in the process of generating Jupiter's magnetic field. Electromagnetic induction in any conducting structure would generate currents proportional to the magnetic flux passing through it, creating forces that would shear any extended structure and heat any conducting material resistively. The electromagnetic environment of Jupiter's metallic hydrogen layer is as hostile to structured matter as the pressure and temperature environment. At the dilute core, the distinction between survival and non-survival is no longer meaningful in terms of physical states that any material can maintain. And the heavy element mixture at the center of Jupiter exists under conditions that define the boundary of what thermodynamics permits for condensed matter. The equations of state that govern material behavior at these pressures and temperatures are derived from quantum mechanical calculations, from the first principles of how electrons and nuclei interact under extreme compression. Because no experiment has ever directly measured the properties of matter at 45 million atmospheres, Jupiter does not merely kill you, it transforms whatever you are into something that participates in its interior. The atoms that constitute your body, the hydrogen, oxygen, carbon, nitrogen, and other elements of biology, would not be destroyed in the sense of being converted to energy. They would be dissolved into the medium, contributing their small mass to the hydrogen-helium fluid, their heavy elements sinking through the metallic hydrogen toward the enriched core, becoming part of the dilute zone of heavy material that Juno has revealed as the heart of the planet. There is a specific poignancy to this that the physics makes literal rather than metaphorical. Jupiter, as a planet, formed from the same molecular cloud that formed the Sun and the Earth and every other body in the solar system. The heavy elements in Jupiter's core, the silicates, the ices, the carbon compounds, were forged in the interiors of stars that died before our solar system formed, scattered through the galaxy in supernova explosions, swept up in the disk of material that surrounded the young Sun. Every atom in Jupiter's core has a history that predates the solar system. And every atom in your body has the same history. At the center of Jupiter, they would mix. You would become part of a planet, and the planet would continue, as it has continued for 4.5 billion years, converting the gravitational potential of its own gradual contraction into heat, warming its moons, shaping the trajectories of asteroids and comets, being the silent giant that made Earth's stability possible. This is what happens if you fall into Jupiter. You fall through clouds of ammonia, ice, and water, through lightning storms more powerful than anything on Earth, through increasingly dense and hot fluid hydrogen, through the transition to metallic hydrogen conducting Jupiter's magnetic field, through the dilute extended core of mixed heavy elements under conditions that no material can survive. And eventually you become part of a world that was here before life existed on Earth, and that will be here long after the last living thing on Earth has gone. Jupiter does not notice. It is, in the truest sense, too large to notice anything as small as you. But the physics of what happens to you, layer by layer, step by step, in the most precise physical accounting available to science in 2025, is exactly as described. And the most terrifying thing about it is not the heat or the pressure or the radiation or the lightning. The most terrifying thing is the absence of a surface. There is no bottom. There is no impact. There is only the gradual, inexorable conversion of falling into dissolving, of motion into stillness, of structure into mixture. Jupiter does not crush you, it absorbs you, and then continues, as if you were never there. Let me go deeper into each layer of this descent, because the overview leaves out the specific physical details that transform an abstract death sentence into something genuinely strange and genuinely fascinating. Consider the cloud layers more carefully, because they are far more complex than the simple three-tier model suggests, and the complexity is where the terror begins. The ammonia clouds at the visual cloud tops are not static, peaceful layers. They are the visible surface of a weather system of extraordinary violence. Jupiter's atmosphere is driven by two energy sources simultaneously, the sunlight arriving from above and the internal heat rising from below. This dual energy input drives weather patterns that have no analog on Earth. The jet streams, the atmospheric currents at the boundaries between belts and zones, move at velocities of several hundred kilometers per hour and have been stable in their positions for as long as Jupiter has been observed. Juno's microwave radiometer has shown that these jet streams extend downward into the atmosphere for hundreds of kilometers, far deeper than any jet stream on Earth, where weather features are confined to the thin troposphere. On Jupiter, the weather goes deep, and the depth means it is anchored by forces that have been in place since the planet formed. The Great Red Spot, the most famous feature of Jupiter's atmosphere, is an anticyclonic storm with a diameter currently approximately 14,000 kilometers, slightly larger than Earth. Though the spot has been shrinking over the past century from its earlier size of nearly 40,000 kilometers. It rotates counterclockwise in approximately 6 Earth days. Its clouds reach approximately 8 kilometers higher than the surrounding cloud deck, making it visible as a slightly elevated feature. The winds around its periphery move at approximately 600 kilometers per hour. The temperature at its center is slightly colder than its surroundings, as is typical for anticyclones. The high pressure at the center pushes material outward and upward, cooling it adiabatically. Falling through the Great Red Spot would mean entering a region where the convective dynamics are different from the surrounding atmosphere, where the organized anticyclonic circulation would carry you around the periphery of the storm rather than straight down. That if the scale of your fall were comparable to the storm's diameter. For a human-scale object falling freely through the upper atmosphere, the fall would be overwhelmed almost immediately by the wind velocity. Horizontal winds of hundreds of kilometers per hour would carry you laterally as quickly as you fell vertically. You would not fall straight into Jupiter. You would be carried along with the atmospheric circulation, moving with the cloud bands, cycling around storm systems, rising in updrafts and descending in downdrafts, until the increasing density of the atmosphere brought your terminal velocity to zero and you became entrained in the fluid. The lightning that surrounds you in the cloud layers is Jovian lightning, and its properties differ from terrestrial lightning in ways that Juno has revealed in detail. On Earth, our lightning initiates in water ice clouds when freezing water droplets collide with smaller ice crystals and exchange charge. The same mechanism operates on Jupiter, but the scale is different. Jovian thunderstorms can be thousands of kilometers across. The charge separation that drives lightning can involve columns of water and ice extending hundreds of kilometers vertically. Individual lightning strikes have been detected by Juno at radio frequencies, consistent with energies comparable to Earth's most powerful superbolts, and the frequency of these superbolts at Jupiter is far higher than on Earth, occurring in the hundreds per second across the planet's surface area. The most striking finding from Juno about Jovian lightning is its distribution. On Earth, lightning occurs predominantly in the tropics, where solar heating drives the convective updrafts that create the charge separation. On Jupiter, lightning occurs predominantly near the poles. This distribution reflects the fact that Jupiter's energy budget is dominated by internal heat rather than solar heating. The poles, which receive very little sunlight even by Jupiter's standards, are still convectively active because the internal heat rising through the planet maintains convection at all latitudes. This planetary-scale convection, powered by the cooling of a world that is still giving off the heat of its formation 4.5 billion years later, drives the weather of a gas giant in a way that has no terrestrial analog. Now descend below the water cloud layer into the region the Galileo probe entered in 1995. And this is the clearest data we have about what Jupiter's interior actually looks like from direct in situ measurement. The Galileo atmospheric probe was a 339-kilogram vehicle that entered Jupiter's atmosphere on December 7, 1995, after a 6-year journey from Earth. It entered at approximately 47.4 kilometers per second, making it the fastest human-made object to enter a planetary atmosphere at that time. The deceleration during atmospheric entry was approximately 230 g-ks, 230 times the gravitational acceleration of Earth's surface, making it the most violent deceleration of any spacecraft ever designed and built. A titanium pressure vessel protected the scientific instruments during entry. After the deceleration phase, a parachute deployed and the probe descended at approximately 150 meters per second, measuring atmospheric properties as it descended. During its 58-minute descent, the Galileo probe found something unexpected. The atmosphere was much drier than models had predicted. The water abundance was far lower than expected based on solar elemental abundances. This was puzzling because water, formed from oxygen, which is among the most abundant elements in the universe, should be present in Jupiter's atmosphere in proportion to its solar abundance, or even enhanced above that if Jupiter formed preferentially from ice-rich planetesimals. The low water abundance suggested that the probe had entered an atypical region, a hotspot, a region of descending dry air analogous to a high-pressure system on Earth, rather than a representative location. Juno confirmed this interpretation. Its microwave radiometer, which probes much deeper and across a much wider range of latitudes than the Galileo probe could access, found that the water abundance increases substantially below the probe's maximum depth and varies significantly with latitude, with the equatorial hotspot region being anomalously dry and the deeper and higher latitude regions containing far more water. The overall water abundance, when averaged globally and at sufficient depth, is approximately 5 times the solar value, consistent with Jupiter having formed from ice-rich material in the outer solar system before migrating inward to its current position. Below the Galileo probe's maximum depth, Juno's microwave radiometer probes continue to return data, not direct measurements of temperature and composition at a specific point as the Galileo probe provided, but remote sensing of the thermal emission from deeper layers, which can be inverted to infer temperature profiles at depths of hundreds to thousands of kilometers. The profiles from Juno's 26 radio occultation soundings, reported in 2025, reveal a latitude-dependent thermal structure with features that persist to depths far below the cloud deck, evidence that the three-dimensional atmospheric dynamics of Jupiter extend through a much thicker layer than was understood before Juno. At the base of the atmosphere, the gradual transition from gas to dense fluid at pressures of around 1,000 bars, the temperature is approximately 1,000 degrees Celsius. This is the level at which the Galileo probe would have been destroyed if it had reached it with its pressure vessel intact. The titanium vessel, however, failed at 24 bar and 160 degrees Celsius, far short of this depth. The probe's final moments, as the pressure and temperature exceeded its structural tolerances, were not recorded. The communications link failed before the pressure vessel failed, either because the high-temperature environment disrupted the electronics or because the antenna pointing was lost as the probe was buffeted by the increasing winds of the deep atmosphere. What happened to the Galileo probe after communications failed is known from physics rather than from telemetry. The pressure vessel, eventually compromised by the combination of pressure, temperature, and corrosive atmospheric chemistry, would have lost its structural integrity. The internal components, the printed circuit boards, the wire harnesses, the scientific instruments, would have been exposed to the high-temperature, high-pressure atmospheric chemistry and would have disintegrated in minutes to hours. The metals in the structure, titanium, aluminum, copper, would have dissolved into the fluid atmosphere, their atoms becoming trace elements in the Jovian fluid, drifting downward with the convective circulation toward ever greater depths. By this standard, the Galileo probe has long since been fully incorporated into Jupiter's atmosphere. Its atoms are now part of Jupiter in a literal sense, distributed through the atmospheric fluid, carried by the planet's internal dynamics toward the deep layers, eventually contributing to the dilute core region that Juno's gravity measurements have revealed. The most scientifically productive atmospheric probe ever sent to a gas giant has become part of the gas giant it studied. This is the fate of everything that enters Jupiter. The descent continues past the metallic hydrogen transition, which occurs at pressures of approximately 1 to 2 million bars and temperatures of approximately 10,000 degrees Celsius. This transition, predicted theoretically for decades and constrained observationally by Juno's gravity data, is not a sharp phase boundary in the way that water freezes at 0 degrees Celsius at 1 atmosphere of pressure. It is a gradual transition, the electrical conductivity of the hydrogen increasing continuously with depth as the electron mean free path decreases and the electronic structure changes from molecular to metallic. There is no surface of metallic hydrogen. There is a region where the hydrogen becomes progressively more metallic, and that region extends through most of the interior. Within the metallic hydrogen, the magnetic field intensity is enormous. Juno's magnetometer has measured the magnetic field at altitudes of 4,000 to 50,000 kilometers above Jupiter's cloud tops, and used these measurements to constrain models of the field generation in the deep interior. The field at the cloud tops is approximately 14 times Earth's surface field, but this understates the field strength in the metallic hydrogen where the dynamo operates. The currents in the metallic hydrogen that generate the field are estimated to involve velocities of tens of meters per second of conducting fluid, carrying currents that, if expressed in terms of the equivalent wire geometry, would dwarf any terrestrial electrical system by many orders of magnitude. The electromagnetic forces in this region are sufficient to influence any conducting material, any metal structure, any spacecraft hull, any pressure vessel, any system with conducting components would experience electromagnetic braking forces from induced currents that would transfer kinetic energy to heat, slowing the descent and heating the structure simultaneously. The electromagnetic environment would complement the thermal and mechanical pressure environment in ensuring that no engineered structure could maintain its integrity. At the center of all of this, back in the dilute heavy element core that extends to 30 to 50% of Jupiter's radius, in the region where the central pressure exceeds 45 million bars and the temperature exceeds 30,000 degrees Celsius, the matter is in a state that has no name that communicates physical intuition. It is not solid because no intermolecular structure can withstand the pressure. It is not liquid in any conventional sense because the thermal energy is so large compared to the interaction energies of the atoms that the concept of a structured liquid has no meaning. It is not a gas because the density is comparable to that of rock. It is a dense, hot, partially ionized plasma of hydrogen, helium, and heavy elements. It is compressed to a density of approximately 5 to 6 grams per cubic centimeter, comparable to the density of Earth's mantle, and maintained at temperatures that would strip the electrons from many atomic species. This is the end of the descent. Not a surface, not an impact. A state of matter for which physics has equations, but human perception has no reference. Jupiter is 4.5 billion years old. It has been this way since before the Earth formed. The same planet that made Earth's stability possible, that shepherded the inner solar system, that is visible as a brilliant point of light in the night sky, and whose 4 largest moons Galileo first saw through his small telescope in 1610. This planet contains, in its interior, most conditions that exceed anything achievable in any human laboratory, and that physics can describe with greater precision than any experiment can verify. The fall into Jupiter is a journey through the complete range of conditions that matter can occupy in the universe, from the cold molecular hydrogen of the upper atmosphere to the dense plasma of the deep interior, compressed into the volume of a world inaccessible only to imagination and to the patient work of instruments that circle at a distance, reading the gravitational signature of what lies inside. Juno has been reading that signature since 2016. Its final orbits in 2025 have added more data, more radio occultation soundings, more gravity measurements, more microwave profiles. The picture it has built of Jupiter's interior is the most detailed ever assembled of any giant planet. It is still incomplete. The dilute core's exact extent and composition remain uncertain. The transition from molecular to metallic hydrogen is not fully characterized. The behavior of the deep atmospheric dynamics below the depths accessible to Juno's instruments is still partly theoretical. But the broad picture is clear. Jupiter is not the simple planet of the pre-Juno models. It is not a compact rock core surrounded by a uniform hydrogen-helium envelope. It is a world of gradients, of continuous transitions, of structures that blend into each other across hundreds of kilometers of depth, driven by an internal heat source that has been cooling for 4.5 billion years and has not yet finished cooling, generating a magnetic field of unmatched power in the solar system, and supporting weather systems that have persisted since before life existed on Earth. Falling into Jupiter is not falling into something foreign. It is falling into the most primordial material in the solar system, the hydrogen and helium that formed from the Big Bang, captured by the young Jupiter before the sun had fully lit up, compressed and heated by gravity over 4.5 billion years into the alien interior that Juno is only now beginning to fully map. You would become part of that, not because Jupiter cares, because physics does. And physics, in the interior of Jupiter, does not negotiate. There is one final dimension of the Jupiter descent that I want to address, and because it connects the physics of what happens inside this planet to a question about time that transforms the abstract terror of the descent into something more personal and more disturbing. Jupiter is older than Earth, both formed from the same solar nebula approximately 4.5 to 4.6 billion years ago, but Jupiter formed first, possibly within the first million to 10 million years of the solar system's history, growing quickly from an initial solid core that captured the hydrogen and helium of the surrounding disk before the young sun's radiation pressure could disperse it. The Earth formed later and more slowly, accreted from rocky and metallic material in the inner solar system over the course of tens of millions of years. This means that Jupiter has been sitting in the solar system, slowly cooling and contracting. Yet for longer than Earth has existed, the heat it is still releasing, the internal energy that drives the convective weather systems visible from Earth, is the remnant of 4.5 billion years of gravitational contraction. Jupiter shrinks by a few centimeters per century and cools by approximately 1 degree Celsius per million years. At this rate, it will continue to emit internal heat for billions of years into the future, long after the Sun has completed its main sequence evolution and entered its red giant phase. The matter at the center of Jupiter has been under extreme pressure and temperature for 4.5 billion years. The atoms there, the heavy elements that settled toward the core, the metallic hydrogen above them, the molecular hydrogen in the atmosphere, have been in their current configuration, participating in the current dynamics, yet being compressed by the current pressure for a span of time that encompasses the entire history of life on Earth. Every organism that has ever lived on Earth, every species that has arisen and gone extinct, every mass extinction and every radiation of new forms of life, every age of dinosaurs and every age of mammals, all of it has occurred while Jupiter's interior has been as it is now, slowly cooling, generating its magnetic field, maintaining its weather systems, orbiting the Sun. And it will continue. When the Sun expands into a red giant in approximately 5 billion years, engulfing Mercury and Venus and possibly Earth, Jupiter will still be there, further from the expanding Sun, perhaps even growing warmer temporarily as the solar flux increases, its moons potentially thawing, and its atmosphere expanding as it absorbs the increased solar energy. Jupiter will not be destroyed by the Sun's death. It will survive as a cold, dark world after the Sun burns out, orbiting the white dwarf remnant of our star for billions of years more. The atoms at the center of Jupiter will be there through all of this, long after every human being who has ever lived has turned to dust, long after the dust of those human beings has been incorporated into geological strata or eroded into the ocean, long after the oceans have been boiled away by the expanding Sun, long after the Earth itself, if it is consumed by the red giant phase, has been incorporated into the Sun's outer layers. The matter at Jupiter's center will still be there, still compressed, still hot, still part of the most massive object in the solar system that is not a star. Yet this is the context in which the fall into Jupiter acquires its deepest meaning. It is not merely a physical journey through increasing pressure and temperature, though it is that. It is a journey into the most permanent object in the solar system, the planet that has been here since the beginning and will be here after everything that currently matters to human civilization has dissolved. Jupiter does not notice the fall. It does not notice Juno orbiting it, does not notice the Galileo probe that became part of it in 1995, does not notice the vast majority of the comets and asteroids that its gravity captures and dissolves into its atmosphere every few thousand years. In 1994, the comet Shoemaker-Levy 9, which had been captured by Jupiter's gravity and broken into 21 fragments by tidal forces, impacted Jupiter over 6 days in July. Each fragment entered the atmosphere and was absorbed, creating impact scars visible in the cloud deck for months. The largest fragments produced impact scars larger than Earth's diameter. Jupiter's atmosphere recovered completely within months and continues today as if nothing happened. Jupiter absorbs things. That is what it does. It is the solar system's largest consumer, a world that has been incorporating material since before the Earth formed and that shows no sign of noticing what it consumes. The fall into Jupiter ends not with a surface impact, but with an absorption, the gradual conversion of an organized structure into the undifferentiated fluid of the Jovian interior. The most unsettling fact about this is not the physics, it is the scale of the indifference. While Jupiter is 1,321 times the volume of Earth, the interior into which you fall contains more mass than 317 Earths combined. The electromagnetic environment of its metallic hydrogen generates a magnetosphere large enough to contain the entire Sun. The weather systems on its surface are larger than entire planets, and none of it registers anything as small as a human being, or a spacecraft, or a comet 20 kilometers across. The scale difference between Jupiter and anything it consumes is so large that the concept of notice does not apply. The planet is not cold toward its visitors. It is simply too big to be anything toward them. They are less than rounding errors in the accounting of a world that has been here for 4.5 billion years and plans to be here for billions more. This is the scary truth about what happens if you fall into Jupiter. Not the specific mechanism of death, the radiation, the temperature, the pressure, the electromagnetic environment. Those are details, interesting in their specificity, but not ultimately the source of the terror. The source of the terror is the scale, the age, the indifference. You fall, you dissolve, you become part of something that was here before you and will be here after everything you know is gone. And Jupiter continues, as it always has, as it always will, the most ancient world in the solar system, turning, cooling, generating its vast magnetic field, maintaining its storms, pulling its moons through their orbits, and never once noticing the things that fall into it, including you, especially you.